What you're looking at here might seem like a simple laboratory setup, but it represents something much bigger, a shift in how we understand measurement, corrosion, and even science itself. Back in the 1970s, engineers discovered a serious problem. Gas pipelines protected using cathodic protection were still corroding and leaking, even though they shouldn't have been. The issue came down to something they called the IR drop, a distortion in electrical measurements caused by resistance in the soil. In simple terms, the readings engineers relied on were not showing the true condition of the pipelines. Large-scale projects like overline inspections were launched to investigate and solve this problem. But even by the third phase, the problem remained unresolved. Scientists had already identified an important clue. If you briefly switch off the protection current, a tiny kick appears in the signal, a moment when the true condition of the metal can be seen. The challenge, however, was that this moment happens extremely quickly and cannot be reliably captured during field measurements. The question then became, how do you accurately measure reality at that exact instant? This is where the Alexander cell comes in. It was designed to remove the distortion caused by the IR drop and allow the true polarized potential to be measured consistently, both in the laboratory and out in the field. More importantly, it provides a way to establish a true zero reference point for measurements. The idea of zero is critical. When using a voltmeter, the device automatically sets its own 0 point, and every reading is based on that reference. However, an oscilloscope works differently. It displays electrical signals as a graph, and the user must decide where 0 is. If that reference point is incorrect, then everything measured from it is also incorrect. On an oscilloscope, this reference point is known as the trigger. It tells the system where to begin measuring. The key breakthrough is that the Alexander cell provides a reliable and consistent way to set the true 0 point. This makes accurate measurement possible and allows meaningful computer analysis of the data collected during surveys. Originally, oscilloscopes worked by firing electrons into a screen, physically tracing the signal in real time. Today, digital oscilloscopes use software to do the same job, but the principle remains unchanged. Without a correct reference point, even the most advanced systems will produce flawed results. While this work began as a solution to corrosion in pipelines, its implications go much further. Modern physics is grappling with questions about observation and reality, what it means to measure something, and how measurement affects what we see. If the systems we use to measure are flawed, then our understanding of reality is flawed. The Alexander cell addresses this at a fundamental level. By stabilizing the point of measurement and defining a true reference zero, it allows reality to be observed more accurately. What started as an engineering solution may ultimately contribute to a deeper understanding of how we measure, how we observe, and how we interpret the world around us.